Hello everyone, myself Deepak Upadhyay from Impulse Technology, Gurgaon, Delhi. Today I will show you how to calculate the electronics property of nickel oxide by using DFT and Howard method DFT plus U. As you know, density function theory is one of the most convenient computational tool for the prediction of property of different class of material. Although its accuracy is acceptable as long as structural and cohesive property are concerned, and it dramatically fell in the prediction of electronics and other property of semiconductor. So to solve this problem, the Howard model DFT plus U introduced, which is computationally convenient for accurate calculation of electronic structure. So I would like to open my device studio. So this is my device studio, that is a user interface for this Nanodical and ASCII software. And this device studio will help you to build your structure. So I would like to click on file, and in the file option you can see this is for creating the new project. You can open your existing project. This is for save the project. Here you can create your new device structure, crystal structure, molecule structure, and this is the import option. This software have two options to import the material. Either you can import the material from local database that exists inside this software. Either you can import the material from online database. So you can click on the import local, and here you can see this is 0D material, 1D material, 2D material, 3D material, and some organic material is there. In 0D material, some molecule, amorphous and crystalline is there. And this is the 1D material where nanotubes, different combination of Kroll vector. And this is the 2D material where you can see some novelty material, arsenic, bismuth, black phosphorus, and this is the graphene. This is the 3D material where you can see conductor, insulator, layer material, magnetic material, metal oxide, novelty material, semiconductor is there. In conductor, this is the conductor, pure metal. This is the insulator, diamond, MgCl2, NaCl2, and this is the layer material. This is the magnetic material. This is the metal oxide. This is novelty material, some perovskite and topological insulator is there, and this is the semiconductor. So the conclusion is all about that. This is the material database that exists inside this software. So I would like to create a crystal structure. So you can click on the file option, go to the new option, and here you can select the crystal. Once you click on the crystal, this interface will open, and this is the crystal builder where you can see some space group, various space group are there, and according to space group the Bravais lattice will automatically selected. And also you can send the ABC value, alpha, beta, gamma value, and here you can select the element. So as per your need you can select the ABC value, alpha, beta, gamma value, and here you can select the element. Here you can see the default carbon atom is selected, but if you want to change this carbon from another atom, so you can click on this carbon, and after this clicking on the carbon, the periodic table will open, and from this periodic table you can select any atoms. And if you want to add more atoms, so here you can click on the plus icon, and if you want to change this nickel with oxygen, so this is the oxygen, and click on OK, and this is also oxygen. And also you can change the fractional coordinate point, whatever point you want. And once you select the fractional coordinate point, you can click on the preview style like primitive cells, conventional cells. So this is the conventional cells. You can click on the preview, and you can click on the build option. So this is the nickel oxide. If you want to simulate this nickel oxide, so you can click on the simulator, you can click on the Nanodical and go to the SCF calculation. So this is the self-consistent field calculation for the nickel oxide. You can select the electron temperature, cutoff energy, exchange correlation function. Also you can define the K point sampling. This is the tension control, density matrix, Hamilton matrix, total energy, and this is the basic setting, arrangement by element, by atoms, and this is the spin type. If you want to include some spin tonics application like collinear spin, general spin, so you can select this collinear spin, and then you click on this generate file. Once you click on this generate file, here you can see this is the project window where your input and output file will be shown. This is the property window where the property of our whole structure will be shown. So once you click on this generate file, here you can see the SCF input for this crystal has been generated. So you can right click and click on the open with. This is the script that automatically generated once you click on this generate file, and here you can see whatever parameter we have defined. This is the basic settings, spin type, collinear spin, iteration control, and this is the basic set. This is the atom and their Cartesian coordinate point. So if you want to run this job, so you can right click on this SCF input and click on the run option. Here you can see if you want to run this job on parallel, suppose 5 core, 10 core, 15 core, so there is no limitation of core. You can define up to 128 cores. So you can click on the run option to run this job. In the bottom of the page you can see this is the job manager where the status of your SCF input is in the running condition. And in the meantime you can select the analysis parameter, whatever electronics property you want to simulate from this nickel oxide. So you can click on the nanonickel and go to the analysis part. So this is the electronics property, whatever property you want you can select. So this is the density of state. Here you can also change the K point sampling, number of energy point, energy range, and this is the projection by atom, by orbital, and then you can click on this generate file. So you can also run this analysis part as well. Right click and click on the run option to run this job. So this calculation is for this DFT calculation, and if you want to calculate the DFT plus U, so right click on the crystal option and copy this project. You can copy and you can rename this project, and here you can see this is for the DFT plus U. Then again you can go into the simulator and select this nanonickel and click on the SCF calculation, self consistent field calculation. Here you can select the electron temperature, cutoff energy, exchange correlation, K point sampling, iteration control, density matrix, Hamilton matrix, total energy, and this is the basic setting. So this is the DFT plus U. So here you can select this Howard U terms, and here you can see some SPDF combination is there, and if you want to change this, so you can also change their coordinate, fractional coordinate point, and here you can also include the spin, collinear spin, and then you can click on this generate file. Once you can click on this generate file, this SCF input for this Howard U term has been generated. You can right click and click on open with. Here you can see this is the Howard parameters, and then again you can click on this SCF input and click on run option to run this job. And in the meantime you can select the analysis part as well. So you can go into the simulator, select this nanonickel and go to the analysis part, and here you can select this density of state, and also you can define the K point sampling, number of energy point, energy range, and this is the projected by atoms, and then you can click on this generate file. So in the same way you can run this job analysis part. So you can wait until the calculation has been finished, and once this calculation has been finished their output file will be generated. In the job manager you can see all the calculation has been finished and their output has been generated. So this is for the DFT calculation and this is for the DFT plus U calculation. So you can click on this density of state, right click and click on show view. So this is the density of state with respect to energy for this DFT calculation, and you can again click on this density of state, right click and click on show view, and this is the density of state with respect to energy for the DFT plus U. So whenever you compare the calculation of DFT and DFT plus U, where you can find DFT plus U has more obvious corrected effect on the size of the band gaps. So in the process of calculation, according to your own research, you can determine whether the calculation need DFT and whether the calculation need DFT plus U. So thank you for watching this video.